to start transformations, one of the things we have to know how to do, or have to not know how to do, but have to know really well, is our parent functions. So in that note sheet that I gave you, one of the sides is to write down your parent functions, and we are going to put those in there, and you are going to draw yourself perfect pictures of each graph, and you're going to give yourself what I call your favorite points. Up here it's listed as your key points. I will give the minimum for that, and if you want to make your list of key points or favorite points a little bit longer, that's great. Not something you necessarily have to memorize, but you'll use them enough that you probably will start recognizing them or knowing the basic ones that we use a lot. Our first function that we're going to graph is x squared. On my key points, I'm just picking x values to plug into the function. My typical ones that I pick would be -1, 0, and 1. And if I plug those into our x squared, -1 squared is 1, 0 squared is 0, 1 squared is 1. And if I graph those points, the only reason I would maybe add a couple points to that graph is if I'm not remembering the shape of an x squared. Okay, as I might add to that list like -2 and +2. -2 squared is 4, +2 squared is 4. And what we end up getting is this nice smooth curve between all of those points. So give yourself your list of favorite points and give yourself a perfect graph to look at. And right now, as you're drawing your graph, what I want you to look at is, are you one of those people that draws points so tiny that as you draw your line through it, the points tend to disappear? And the only thing I would say is, as we're doing this transformation chapter, that's probably not going to be in your best interest, as I would draw your dots a little bit bigger, because our graphs need to be perfect, and the dots are kind of where it's all at. So make sure you can kind of see your dots as you are doing that. And like I said, you can make this list of favorite points longer if you want to add the -2 and 2 in there as well. That's for you, and it's going to mean a lot more to us tomorrow. We really don't use them much today. Tomorrow we're going to just rely on those tables of points a lot. And you kind of need to be able to create those quickly as you do each problem to be able to graph and do transformations. Okay. All right, so our next parent graph would be an x cubed. Same 3 favorite points on this one, -1, 0, and 1. And if I put those each into our function, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1. That is not going to show you the shape. So if you do not remember the shape of an x cubed graph, you might need to expand that to -2 and +2. It kind of looks like a straight line in here. But if I were to look at -2 cubed, which is -8, and +2 cubed, which is +8, mine kind of run off the graph here. But what it does is it starts getting really big really fast, squiggles through the middle of my graph, and then continues getting really big really fast. So there's a picture of your x cubed graph. Okay, our next one would be our absolute value graph. Same favorite points, and again, as I do this one, if you need to add more points to see the shape, if you know the shape of an absolute value graph, the middle 3 will be plenty, but if you need a few more to remember your shape, the absolute value of -1 is 1, of 0 is 0, and of 1 is 1. It looks like the start of that parabola as well. If I were to expand this out to like -2 and 2, it would start showing our shape a little bit more, and our absolute value graph is just a V with a sharp corner at 0, 0. Okay, our next one. Now this one is a little unique in our table of points. I'll list 3, but we actually kind of highlight 6 points in our graph, but because it's like a duplicate, I don't necessarily write them out each time. And I'll explain to you, I'm strategically picking my points on this one to see the shape of our graph. The first point I always start with is 1. If I were to plug 1 into this graph, we get 1 over 1, which is 1. So I go over 1, up 1. The second one I always pick is 2. If I were to plug 2 in for x, I would end up with 1 over 2, or a half. So we go over 2, up a half. And the last one I plug into this one is actually 1/2. And I just want to show you the algebra behind this just so it makes sense. If I were to plug in 1/2 where the x is, I get 1 divided by 1/2. And remember that when we divide by a fraction, it's the same thing as multiplying by its reciprocal, right? So this is the same thing as 1 times the reciprocal of 1/2, or 1 times 2, which is 2. So that's why I get an answer of 2 when I plug in 1/2. So over 1/2 up 2. The graph then slides along my x or y-axis, goes through those 3 points, and then slides along my x-axis. So the 3 points are just kind of helping me with the corner part on this. That's half of a 1 over x graph. The other half comes from plugging in negative numbers. Well, when I go to the other side, I plug in the same 3 x's, except for I plug them as negative numbers. So like if I plug in -1/2, well, my result's going to be -2. If I plug in -1, the result is -1. And if I plug in 2, the result is -1/2. And I get those same 3 points in the corner, but in quadrant 3 instead of quadrant 1. Slide along my axis, go through those 3 points, slide along my axis. And the combination of those two pieces is your 1 over x graph. Okay. Now, with that being said, as we apply our transformations, although it's not a piece of the graph, I kind of consider the middle part right here like this is where I kind of base my graph off of, and from the origin I go over 1, up 1, over 2, up 1/2, over 1/2, up 2 to get those 3 points. Well, when I do my transformations, I kind of just pay attention to where that middle moves as well, because it would move the same as the rest of the graph. And you can then just repeat that pattern. Like let's say that middle moves left 3 and up 4. I just kind of recreate that for myself, and then I go over 1, up 1, over 2, up 1/2, over 1/2, up 2, and I can draw in that same corner up there as I did around our origin, which is going to make more sense again as we practice some more of our transformations. Next parent graph, square root of x. On this one, we have to pick our x's strategically. First of all, it has a domain restriction, so I can't pick all x's. I can only pick positive numbers and 0 is where I start. Square root of 0 is 0. Then I go in the positive direction. Square root of 1 is 1. And I can pick 2, but I don't know off the top of my head what that is because it's a really ugly number. Square root of 2 is some decimal. So then I just jump to the next one that's going to give me a pretty answer. What is that next number that's going to give me a pretty answer? 4. So then my table looks like 0, 1, 4, and the square root of 4 is 2. So our next one is way off my picture. The next nice pretty one I would pick would be like 9, right? Square root of 9 is 3. This one starts at 0 and then just nice curve slowly increases as you go to the right. Okay, cube root. Same idea for our cube root as I kind of strategically pick my x's to put in the table. This one does not have a domain restriction, so you can and will want to pick negative numbers. Again, if I pick just the -1 to 1, you don't really see the shape. So either you need to remember the shape or pick a couple extra numbers in your table. The cube root of -1 is -1. The cube root of 0 is 0, and the cube root of 1 is 1. And we see the same 3 dots that we saw when we did our x cubed graph. So that's where we might need to check a couple others. Well, because I'm cube rooting it, I would pick strategically again. The number I want to cube root, I would want to be a perfect cube. So like if I expanded this, the next x I would actually pick would be like -8 because it has a nice clean cube root, or +8. Those are kind of off of my graph here, but -8 would be over here-ish. +8 would be over here-ish. And you can see that this increases very slowly, squiggles through the origin, and then increases slowly forever. So that's your shape of a cube root graph. Okay, we're going to pause there. The 6 graphs that you have on your paper right now are the 6 you need to know. Okay, those are the ones that we will use. Those are the ones that we are going to apply transformations on and continue to use for the rest of this section. The next 2 that I'm going to put up here, it is true. They fall in this category of parent functions, but you spent all of Algebra 1 and Algebra 2 graphing linear equations. We're done with that. We're moving on to things that are not linear. So this would be a linear equation. We most often saw it in the format y equals mx plus b. This is the basic one, where b is 0 and your slope is 1, goes through the origin with a slope of 1. I don't even really need favorite points on this one. We know how to graph something like that through the origin, up 1 over 1, right? And it's just a straight line. Like I said, yeah, I'm going to add it to our list of parent functions, and that's about the last time we're going to look at a linear as we talk transformations this chapter. And then the last one is also same idea. It's also a linear equation, except for it's equal to a number. So this would be constant is the same thing. When they say constant, it's just some number, no variable. Or what we're used to seeing it as is y equals some number, okay? And that's just a horizontal line. True, you've graphed those a lot in Algebra 1 and Algebra 2, so we are kind of done. I would not pick any key points on this one. Again, it's just a horizontal line, and that's about the last time we're going to talk a horizontal line. Okay, so as you sit down to do your assignment tonight, you'll want to take your favorite points from that sheet to apply your transformations for. We will continue to add to this sheet as we go through the rest of today, and then tomorrow we will finish out the rest of this sheet as kind of all of our summary rules for transformations. So the one transformation we're going to look at today is our shifts. So if you will grab your graphing calculators, and please type those 3 equations into y1, y2, y3. Look at them, see what's going on, and see if we can figure out what those numbers do to our function. Make sure you type it in just as I have it up there with the parentheses and everything. If you have a nice color calculator, you may help your table partners as well. Let them look at yours because it's easier to see on there. But let's talk as a table. Once you get them typed into your calculator, talk as a table. Give me like a generic, what are those numbers doing to our graph? And then the other thing I want you to talk about is, does it move the way you think it would have? Does it move the way that like your intuition says it should move? Okay, generically speaking, what are those numbers doing to our graph? Moving them left and right. Okay, so then if my question makes sense, does it move it the way that you feel like it should? Like when in your head, when you think the direction left, do you think positive or negative numbers? Negative. Did the negative move left? No. So it's not actually moving the way that we probably think in our head, because negative we think left, positive we think right, but inside of our function everything is always opposite, and that's going to be an underlying theme for all of this. So you can see on this one I kind of have them color coded here. The one that moved us right actually had a negative in it, but we moved to the right 3. The one that had a plus in it moved us left 5, and that you're going to see that for this entire section always. When things are inside our function, they always move opposite of the way we think that they should. Okay? So this kind of summarizes what we just said. If we are adding or subtracting a number on the inside of our function, it's going to move us right or left, and then all kind of opposite of what we think. A plus will move us left, and a minus will move us right. All right, grab those calculators again. Changed it a little bit on you. Notice these ones don't have parentheses. Go ahead and type those in and see what they are doing to your graphs this time. What changes now that I don't have parentheses Exponent is directly on the x. Okay, talk to your table. Where did your graph move? Does it move the way you think it should based off of it being a plus or a minus? All right, generically speaking, outside of that parentheses, which directions are we moving? Up and down. The way we think, negative correlates with down, positive correlates with up. So kind of the signs match the words, right? What we would think those words are doing. So again, kind of summarizing what we just talked about when we're adding or subtracting a number, and that's what I would consider outside of our function. It goes up or down. Positive being up, negative being down. Those are the only transformations we're going to look at today as we kind of get used to. So your job today is to know your parent functions. Know your favorite points on your parent functions. Be able to create that list or know those lists of your favorite points. And then apply these basic transformations to our graphs given an addition or subtraction. One of the things we need to talk about, though, is on both of those we referred to things being inside or outside of our function. Some functions, it is super obvious what would be considered inside compared to outside, and some functions it's not. So we're going to take a second and just look at the 6 functions that we're going to graph. X squared, x cubed, square root, cube root, absolute value, and your 1 over x, and talk about what's considered inside and what's considered outside when looking at those functions. I will tell you that the top row and the bottom row are always the ones that we have hesitations on because it's not as obvious. The middle two, it's pretty obvious what's inside or outside because it's like physically inside or outside of the symbol. So when you are looking at exponents, and notice I grouped those two together because it doesn't matter if it's a squared or a cubed. If we are talking exponents, to be inside of your exponent, you have to have parentheses. Okay, for a number to be considered inside of an exponent, it must be in parentheses. For example, something like x plus 1 cubed, the plus 1 would be considered inside of that function. To be considered outside of the function, it would not be grouped with parentheses, and that exponent would go directly on the x and then some number following that. So the minus 7 would be considered outside of an exponential, where the plus 1 would be considered inside of an exponential. The next two are pretty obvious because there are symbols, and if it is inside the symbols, it's inside. If it's outside the symbols, it's outside. So an absolute value, an example of something inside of your absolute value would be like this minus 3, x minus 3, compared to an outside would be something like absolute value of x and then the plus 5 on the outside of it. Same thing for your square root and cube root. If it is underneath the symbol, it is considered inside. And if it is not, we would consider it an outside number. So something like cube root of x plus 8, that plus 8 would be considered inside, compared to something like square root of x minus 10, that minus 10 would be considered outside. And then we get down to the fraction, and like I said, the exponents and the fractions are the ones where we sometimes have hesitations about the whole idea of inside versus outside. For a fraction to have something that is considered inside of the function, we would find it located in the denominator with the x. Okay, so if we have something like 1 over x plus 9, that plus 9 would be considered inside of this function. If there is something that is outside of a fraction, it would be like separate from the fraction. For example, 1 over x minus 5. That minus 5 would be then considered outside of a fraction. Any questions on the idea of inside or outside? Okay. The last thing is on the back side of your sheet that has the parent functions on it, we've got this thing, a little mnemonic device to help us remember what we just talked about today. I read it as ILROUD, L-I-R-I-L-R-O-U-D. If you can't spell it right, it doesn't help. So it helps you remember what we just summarized, and that's inside and outside. Inside, outside, left, right, up, down. And it always goes in order, plus, minus, okay? So you'll notice on the back side of that, it is listed at the bottom of that sheet, right? It's at the very bottom of your summary sheet on the back, and that's because as we get multiple transformations by the end of tomorrow, it's actually the last transformation that we do. But just a reminder that if a number's on the inside, a positive will move it left, a negative would move it right. If it is on the outside of our function, a positive would move it up, and a negative would move it down. Tomorrow we'll fill in those top 2 types of transformations to get all of the possibilities and how we can then apply multiples to one function. Today, the basics. So let's look at one example of graphing with a up, down, right, left type of transformation. It says use the graph of f of x equals x cubed to graph the following. Today it's going to ask you in your assignment to graph both, which is fine because I actually think it's easier to do that. You graph the parent function. So our parent function x cubed, if I go to my table of favorite points, x cubed still gave me -1, 0, and 1. It looked like these 3 points, and actually if I put the -2 and +2 in there, if I cube them, we get those 5 points, okay? When you're doing ILROUD, inside, outside, left, right, up, down, I really think it is easiest to dot out the graph and count. And so then I go to whatever function I'm trying to be graphing, which is this one, f of x equals x cubed minus 4. Is that minus 4 inside or outside? Outside, which tells us to move our graph which direction? Down. That's outside, so it's going to be down 4. So all I'm going to do is I've got 5 points in my picture, and I'm going to go to each of those 5 points and count down 4 and regraph it. So I'm going to go to this point and go 1, 2, 3, 4. That's where it would be after a transformation of down 4. Go to this point. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This one goes off my graph, but 1, 2, 3, 4. Those green dots are the green graph that has been transformed down 4. When you get to the right, left, up, down, I really think that's the easiest route, is to just put what you have out on the graph and count and regraph the new dot, okay? A second method is knowing whether it affects your x column or your y column, and then just going, this would have affected our y column, vertical, and subtracting 4 from each of those. I just think that that's harder and more confusing. If you really like that, you are welcome to use it as long as we're getting to the right answer. I don't care. All right, and then the last type of question you're going to see today is kind of going the opposite direction. They give us the picture of the resulting graph. We're coming up with what the equation was. So it says, describe how the graphs of f of x equals x squared and g of x are related. Well, the one we're looking at in the picture would be g of x right here, okay? And then write the equation for g of x. So what you're going to do is go look at the parent function. So if I were to put the parent function on this picture, x squared looks like this, right? The easiest way to do this is just kind of find one of the points that you can follow. So like if I were to highlight maybe where 0, 0 started and then where that same point ended up, it's kind of easier to then identify how it moved. How did I go from 0, 0 to this guy, and think through, did I move right or left? How far? Did I move up or down? How far? And that answers the first question, describe how they are related. Okay, so answering the question, this is where I start, this is where I end, did I move right or left? Right. How far? 3. So we move right 3. Then I look for the up or down. Did we move up or down? Yes. Which way? Up. How far? 2. That's answering how, describe how they are related. Done. Then I go to Ilroud to help me write this into an equation. Okay, well, I know it is the function x squared. I also know there's an inside number, which is why I put a parentheses there. My inside number comes from right 3. And I go back to the fact that right on the inside looks like a subtraction. So it's going to say x minus 3. And then to represent up 2, that's outside my function, positive 2. Questions on that? All right. Your assignment tonight is out of the book. You do need graph paper. There are 6 graphs on here. You need 7. So you can draw your own off to the side, or you can do 2 problems on 1 graph. Either way. There's also plenty of white space off to the side to be able to do that 20 through 23. So you can do the entire assignment on this piece of paper so that you don't need to grab another piece of paper for yourself. We also have way more work time than I've given you all year. So let's go ahead and get our assignments finished, started or finished, while we're in here.